Hello and welcome to today's remote class, unfortunately. Today there's two things that I want to get through, and one of them is kind of to give you a little bit of information about using microcontrollers in your designs for your projects. The other thing that I want to get through today is talking briefly about the project proposal and what you are expected to do for submitting that. So let's first get through the little presentation today, and maybe it'll give you a little bit of a better picture of what it is that you can do with microcontrollers and why we're doing things with microcontrollers. So let's go ahead and get started with that. All right, so first off, the first question that might come to mind is like, well, why use a microcontroller for your design? And the idea there is really depends on the project that you're doing. But the idea is, well, a microcontroller being an entire computer system all in one kind of single chip that gives you a lot that you can do with one single simple circuit. And inside of the microcontroller, to give you an idea of everything that's inside of that one little chip, it's a processor, which may be a single core processor, maybe multiple cores. It might be an 8-bit or 16-bit or 32 or 64-bit or even higher microprocessor, but that's in there. There's also memory. And really, there's usually multiple kinds of memory in a lot of microcontrollers. So, for example, there's like flash program memory, just like you have a flash drive that you would plug into your PC to save files on. So there's flash memory that's usually to store the program and maybe other data in. There's RAM. That's just a kind of working memory as it's running, just like your PC has RAM. There's usually also on some microcontrollers Eeprom, which is an electrically erasable programmable ROM, which is kind of like Flash, except that it usually has a higher number of rewrite cycles, so you can use it to store things like settings or remember the state when the thing was turned off. And so there's all those different kinds of memory in there as well. There are peripherals like general purpose input and output peripherals to change the state of pins, turn them on, turn them off, pulse width modulate them, things like that. There's A to D converters in there. Some microcontrollers have D to A converters. Most of them have some sort of timers and counters, so you can make things that happen repeatedly, or you can time things. Or speaking of pulse width modulation on the I/O, there's some of them that have units that do all of that automatically. There are usually several kinds of communication interfaces, SPI, I2C to talk to other components or other devices, USB a lot of times. Other ones will have like a UART to talk over a serial communication link to other things. And some microcontrollers even have wireless capability built into them. As far as the wireless chipset that allows you to talk to that. So some microcontrollers you can add an antenna and maybe a little bit of external circuitry, and now you have this wireless device. Also, some of them have real-time clocks, so not only can you keep track of like a timer counter, just ticks of something ticking, but maybe like the actual date and time as part of that. And a lot of them have special kinds of peripherals as well, like DMA, direct memory access controllers, things like that. All right, there's also a lot of times inside that one single chip, some of the support circuitry you need, meaning some of them don't need a crystal. There's an RC oscillator, or if they do need a crystal, the crystal oscillator circuit that makes the crystal kind of ring and to make the clock tick, 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 that's built in. Some of them have brownout detection, so as they start to lose power, they can detect that power is being lost and then save their settings or do something to put it in a safe state. And a lot of them have what are called Watchdog Timers. And Watchdog Timers, for example, are something that if your code locks up, the Watchdog Timer will expire, and then it can initiate a reset. So if you're using this in an embedded system, the last thing you need is for it to lock up indefinitely and then not work anymore. So a lot of them have a Watchdog Timer capability to kind of handle cases where something would have locked up. And then cache and other things are sometimes in there as well. So in other words, there's this really capable system on a chip with a whole bunch of different stuff. And depending on the microcontroller, there's more A to D converters, more I/O, different timer counters, different communications interfaces. They're all kind of different. So you need to pick the right one for your project you're working on. But the idea is this is incredibly complicated, and I shouldn't say complicated, incredibly feature-rich set of things that are inside of microcontrollers, and you get all of that stuff inside one chip. And that can be really beneficial because you have a small chip count, means small amount of space, means small cost to manufacture. And so these are really good to use in a lot of projects. And in fact, projects that used to be done with other discrete components are now a lot of times being done with microcontrollers because it's just easier and more cost effective to do so. Now, going on, another reason why would we use something like this? Well, microcontrollers can have this wide range of capability. So in other words, the size, meaning how physically large is it? Is it large? Is it small? Some of them are very tiny. How many pins do we need of I/O? If we only need a couple, maybe we'll use the one that's a smaller size, smaller pin count than something where we need a whole lot of I/O. The other thing is computing power, meaning how fast do we need it to compute things? Do we need something that's lightning fast for a real-time application, or something that's handling a whole lot of data, like a video stream or something like that? So the computing power comes in two forms, kind of the clock speed, how fast does the clock tick, and then the architecture, how much work does it do for each of those ticks of the clock. And then there's also this power consumption thing there. Like if you're making something that's battery powered, clearly long battery life is advantageous. So you might use something that has low power consumption compared to something that has to be very quick and responsive and is going to be plugged in rather than running off of a battery. It might not be as important if you're plugging it in as if it's running off of a battery to save power. So there's a balance there between a lot of these different features that we have, including cost and what peripherals there are, how easy is it to use. So choosing that balance of cost versus performance versus your project's needs versus how much power, a lot of that is finding the right microcontroller for the right application becomes very important at that point. Now, one of the nice things that makes that easier, though, is because if we're looking for the right balance in a lot of these different variables, then it's nice to have a lot of choices. And it turns out that there's tens of thousands, really hundreds of thousands, if you count all of them, options to choose from. And so if you just go to a large distributor like DigiKey, who's a large electronics distributor and broker, and you just type in MCU, which is what I did here, notice we get just embedded microcontrollers in that category. There's almost 90,000 choices there. And these are individual product items. It's not like they have just 90,000 microcontrollers in stock. This is 90,000 distinctly different product choices to choose from there. And that's not all of them. If you look down here, here's embedded microprocessors. There's a few of those. Here's RF transceivers. There's 2,600 of those, but a lot of times these include a microcontroller in them as well. So these are those wireless ones I was talking about, and these system on a chip things down here, 2,600 of those. And then down here, embedded application-specific microcontrollers. Those are microcontrollers that are designed for some very specific thing. That might be, I don't know, smart cards, or it might be something to do with video processing, or something to do, in some cases, like wireless stuff of a certain type. But these are microcontrollers that were designed for a very specific purpose. And then they have extra circuitry in them that suits that purpose. But notice there's 2,300 of those. So if we added all this up, so there's 90,000, there's like almost 95,000, and we're over 100,000 choices of microcontrollers to choose from. And that's just from DigiKey. That's not all of them that exist from every company. That's only the ones that DigiKey has in their catalog right now. Now, let's look at kind of the range of possibilities here. And let's start at the low end. So what I did is I searched for microcontroller, and I sorted based on price going up. And you'll notice that here is a 6-cent microcontroller. It's an 8-bit microcontroller, has 1K of flash. So it's got very small program space. And if you notice, well, how much memory does it have? How much RAM does it have? It's only got 128 bytes. But for a very simple project, this might be what you need. And notice it does have peripherals. It's got this power on reset, pulse width modulation, a Watchdog timer. That's what WTT stands for. LVD is low voltage differential. So there's a whole bunch of things that this microcontroller has in it. Not a whole bunch, but enough stuff. But notice it does have an A to D converter in it. It's got other things in it as well. The oscillator is internal, so you don't need any external parts. But this, for 6 cents, you get something that can do 10 million operations in a second. And it's got 13 pins of I/O. And if we go up to this other one that's 6 cents, here's one that runs at 20 million operations per second. It's a 16-bit architecture. It has UARTs in it. It has I2C. It has this LIN bus thing in here. And notice that it's got 128K of program memory, 7K of RAM instead of 128 bytes. And notice it also has an internal oscillator. It's got 6 A to D converter units, and it has 22 general purpose ICs. 6 cents, that's a lot of stuff you can get done with a product like that. And you'll notice that is, looking up here, the same price as that one. And then notice there's some other ones down here. Here's a ST72 for 14 cents. So really for just a little bit of money, you can get a pretty decent amount of processing power that can do a lot. You can do a lot with it. Now let's go more toward the high end. And these aren't the highest end ones that are available. But you'll notice here, I searched for that and looked at some that would make sense. But here's like a $42 microcontroller. And notice it's a 32-bit architecture, and it's got 32 cores in it. So think about your PC with, I don't know, 4 or 8 cores. This is a 32-core microcontroller for $42. And notice it has 176 I/O pins. It's got USB in it. It's got 2 meg of program space of flash, and that might not seem like a lot by your standards for a PC. But in a microcontroller world, that is, and it's got 1 meg of RAM. And so this is like a massively parallel architecture where you have a whole bunch of like really processing units inside of this one chip. So this could be a really useful thing for something that needs to be super fast and come up with calculations where it's doing more than one thing at a time. And so looking at that, $42 might seem pricey compared to the 6 cents we saw in the previous one. But when you consider all of this is a 32-core architecture. This is actually a pretty remarkable chip for that. Now, it is in a package that's a hassle to solder, this 374-pin BGA package. And I don't know if you're familiar with packages, but that's a ball grid array. So if you look on the bottom, it's got a whole bunch of little balls on the bottom, then you solder it onto some board. And notice that this does not have an internal oscillator. You have to clock this one externally. But it's kind of fascinating that you can get this 2000 MIPS chip with 32 cores for $40 essentially. So in other words, this is like 32 different processors all inside of that thing. Okay, now the number of options that we have there can sometimes be overwhelming. And different manufacturers have different product lines, different product families, their own development environments, their own libraries, their own circuit requirements. So sometimes when you pick a microcontroller that seems perfectly suited for the task, you also have to evaluate what are the tools like, how easy it is it for me to set this up? Are the tools free and open source? Do I have to buy some kind of tool chain in order to use this thing? And one of the things that most of the development for microcontrollers has in common, that even though the environments and libraries can be significantly different, almost all development at the embedded level for microcontrollers is done using C language. Now, if you get to some of the higher end microcontrollers, they might run a version of Python or something else. But for the most part, all microcontroller development is done in C language. And the reason for that is C is really in a sweet spot for giving you low-level access to do things at kind of the hardware level, unlike other languages like, I don't know, Java comes to mind. Other languages come to mind as well, like Perl. You wouldn't really use that on a embedded system. But the interesting thing about this is that C, if you learn C programming, that applies to pretty much every one of those 100,000 devices that you would ever use. Hold on a second, I have to go out of frame. I was fidgeting with the thing that I designed in Arduino. All right, now so C can be a good thing to learn. It's a it's a structured imperative language. It's a little different than programming and some other things because you have to really understand things like pointers, which are variables that hold addresses. But if you learn this, it unlocks the door to program any of those hundreds of thousands of microcontrollers. All right, now if you're developing developing some mass-produced product, then you're going to want to select some microcontroller design around that. But one of the things that I want to point out is that if you're at the prototyping level, a lot of times you just want to get the idea working. You'll use something that is not the perfectly tuned microcontroller. You use something that's maybe it's optimized to ease your development rather than optimized for cost or size or battery lifetime. And so that's what we're going to focus on today, because I don't know that any of you right now are interested in developing a mass-produced product where you're going to make 100,000 of them. And if you are interested in that, you still got to make a prototype first and then refine that prototype. So we're going to focus today on some simple to use board designs rather than picking out a microcontroller, designing it into your board, and doing that. I'd suggest you start out with one of these microcontroller solutions that makes it easy to do prototyping development rather than final manufacturability analysis in a mass-produced product. Okay, so for prototyping options, it makes sense to use something that's a pre-designed development board rather than designing your own from scratch, at least at this level. Now, if you are interested in designing something from scratch, you can still do that. It just takes a little more effort because you're going to have to learn what the support circuitry that particular microcontroller you want to use needs. Like, what does it need for a clock? What does it need for a power supply? Does it need a special reset circuit? Does it need special capacitors for noise filtering? You'll have to learn all of that stuff. And then build that into your design, and that takes time. So if you use a board that's already designed to do that, you can get to a prototype more quickly because they've already done a little bit of the engineering for you. So for low volume applications, even things that are commercial products, it's okay to use a pre-engineered board and build your product around that. But if you're going for mid volume here, meaning maybe hundreds to thousands of, and then high volume, meaning probably tens of thousands to hundreds of thousands of units. If you're doing that, then you probably want to go to a custom design board, because that way you can really value engineer it, get the cost down to a point where if you're making 1 million of something, saving a couple cents here and a couple cents there and getting that up to 50 cents is a lot of money. It's $500,000. But if you're making 10 of something, then the amount of effort you would put into doing all that, or making 1 of something, the amount of effort you'd put into value engineering might not be worth it. Okay, so let's look at some of these pre-engineered boards. And there's several options for those, and we're going to take a deeper dive into a few of these, but one of them is Arduino boards, and maybe you've already heard of those or played with those on other projects. But it turns out that there are a lot of boards that are Arduino environment compatible. And what Arduino is, it's a development environment that you can write your code in, upload it to your some microcontroller target solution, some sort of board. And then what Arduino does a good job of is it kind of abstracts some of the things that you might need to learn about if you're doing it directly. So for example, setting up the clocks, setting up the peripherals, how do you set it up to communicate, how do you get code into it to program it. Well, an Arduino just has an environment, you write your code, you click play, and it handles a lot of the stuff. It abstracts away a lot of the stuff so you don't have to worry about it. We'll take a deeper dive into that a little bit. The other nice thing about Arduino is it is an open, the Arduino boards are built on open source hardware, so you could design your own and look at how it works. And it's also open source software, so you could look at how their bootloader works, and you could essentially, it's all wide open for you to look at and modify if you wanted to or needed to. But it also means that you're not paying for anything. It's essentially a free download with free software. The hardware is not free, but the software that runs on it is. Now, Raspberry Pi is another one. That's a full system on board, and it's actually quite powerful. And that system includes an operating system. It includes some advanced peripherals. It has Wi-Fi, has Ethernet. It's got camera interfaces. There's several versions of that as well, but we'll look at that a little bit deeper later. Now, there are some other ones that I want to mention here. There's this thing called Msp Launch Pad Boards. And what the Msp Launch Pad is that's a Texas Instruments specific form factor, but those are low power boards. They have a programmer and a target microcontroller on one board. And so there's a little part of the board that acts like the programmer that programs the other part. And the cool thing about that is if you did want to move towards a mid-volume or higher volume part, you could actually use the programmer on that board to program an in-system microcontroller as well. So it's easy to move towards a full build version of that using that in-system programming capability that the programmer portion of the board allows you. So in other words, rather than having it program the chip that's on the board, you can have it program a chip that's in your design somewhere else. There's some other things like that as well. There's this Pinguino PIC32 that's based on the Microchip Corporation's PIC32 architecture. And those are in an Arduino-like form factor, but they're programmed directly in C rather than the Arduino environment. At least they were last I looked at them. There's also the STM32. That's a company called ST Micro. And that's very similar to the Launchpad, but it supports the STM32 32-bit microcontrollers. And there's a whole family of those that covers the range of low cost, low pin count, all the way up to higher performance ones. And so that also includes an onboard programmer, so it eases the transition from, again, prototype to product very easily in ways that some of the previous things do not. A couple other ones, Teensy. Teensy is a range of small but fairly powerful microcontrollers, and those are compatible with the Arduino environment. And then there's these expressive chipsets, the ESP32 and the 8266 series. And those are microcontrollers, like I said earlier, there's some microcontrollers have wireless built into them. Those two chips actually have wireless or Wi-Fi and Bluetooth capability built into them. And they have open source development tools, or you can do your development through Arduino. So it's kind of like a mixture of some of those previous ones where you can do development directly in C, or you can use the Arduino environment, which kind of hides some of the details of that for you, makes it a little easier. But those boards, for the amount of processing power and capability you get with wireless, at $4, it's a really, really compelling kind of cost to performance ratio. And then there's a whole lot of other ones as well. Like there's a thing called the Beagle board. Intel has a couple, Edison and Galileo, that are kind of like Arduino-like platforms. There's a SparkFun Edge board that's good for AI projects and so forth. There's a whole bunch of those. Just like the hundreds of thousands of microcontrollers, there's probably thousands of these development boards to choose from. Now, let's take a deeper look into a few of these. So let's get started with the Arduino. And specifically, let's look at the Arduino Uno, which is a board that's widely available that some of you may have seen before. And again, why are we using this? Why would you use something like this Arduino? Well, again, that microcontroller combines this rich set of peripherals with a processor, with a memory, multiple kinds of memory, RAM, and the program memory. And so it makes it a really good choice for systems that would otherwise require a lot of circuitry. You could replace, boards this big with dozens of chips on it with one single microcontroller. And they're also very cost effective for two reasons. One is they replace a whole bunch of chips with one chip. The other one is that the more parts you have to place on a board, the more the cost of circuit board real estate is. The bigger the board, the more it costs, the more time there is soldering it, the more expensive it is to make. And then the other part about microcontrollers that makes them valuable is that because there are hundreds of thousands of choices, there's a lot of price competition there, so they tend to be very low cost. Like, for example, if you think back to that 6 cents for a microcontroller that includes a 6-channel A to D converter. If you just go to buy an A to D converter, it's going to cost you several dollars for the cheapest ones you can find. You can get a A to D converter in a microcontroller with memory, with a processor, with a whole bunch of other stuff, with a crystal oscillator, all of that stuff for 6 cents, including the A to D, but you can't buy just the A to D for less than, I don't know, $4 or something like that. And the reason for that is kind of just the economies of scale. That those microcontrollers are valuable for a lot of devices. Almost everything you see is likely to have a microcontroller in it because it's the right choice for development, and because of that, supply and demand. There's a lot of competition. There's a lot of supply. There's a lot of volume going on there, so those can end up being less expensive to buy an A to D converter with everything else in a microcontroller than just the A to D converter. Now, one of the other things that's useful about microcontroller-based systems as opposed to discrete circuit systems is that since they're programmable, you can actually change the program and make it do something different. And there can be a lot of advantages to that. One would be you could have different levels of your product. In other words, you could have a product that has simple features. That's a different program than one that has the professional version or more complex features. So you could use the same microcontroller in a family of your products that you're designing and just put different programming on them. The other nice thing is if you need to do some sort of bug fix or you want to have upgrades, this allows you to do that without completely redesigning a circuit. So if you did this with a discrete circuit and you wanted to make a change, you've got to redesign it. You've got to essentially throw out the old ones and replace it with an entire new one. Where a lot of times with changes with a microcontroller-based system, you can just update the programming. Now, some circuit things might still need to be updated, but it's not quite as simple as that. But it could be that you just update the programming, and a lot of microcontrollers offer what's called Isp capability, or in-system programming, which means that you can take a program and update it, like updating the firmware of your product in the field. So in other words, you could push out those updates to products that somebody's already bought, so they could have the latest and greatest or the bug fixes or whatever, without having to bring it back in and reprogram it and send it back out again. You could do it in the field. Okay, so we talked about why use a microcontroller, but there's also a little bit of discussion of why not use a microcontroller. Are there cases where you would not want to use one? And the answer is yes. So some cases where discrete circuitry is still necessary would be very simple systems. So if you wanted to make something where, I don't know, an LED blinks and it blinks at a different rate depending on, I don't know, some light conditions or something like that, or how close something is to something else. Maybe use a microcontroller for that. Maybe you just use a 5-5 timer and a photocell. I don't know. But there are cases where very simple systems can be more cost effectively built using just discrete circuitry. Although those are getting less and less as microcontrollers get more and more powerful and less expensive. Also, to interface microcontroller systems to real-world devices, like things in the real world, like a machine or a piece of hardware, you're going to need some circuitry to connect that microcontroller to things. Also, maybe to augment a microcontroller-based system. In other words, maybe there's part of it needs to be in analog circuitry, like audio. Part of it needs to be in the microcontroller to do the audio processing of that. I don't know, maybe you're an audiophile and you want to make like some sort of preamp that has tubes in it. But you also still want to have digital effects as well as the tube amplification. For the kind of supposed warmth and richness of the sound, you have the tubes, and for the digital signal processing, you have a microcontroller. And so maybe you have to mix some analog stuff with some digital stuff sometimes. And also for ultra high performance systems, sometimes microcontrollers just might not be fast enough. So things like, I don't know, like a guidance system and a cruise missile or something like that, maybe parts of that need to be analog circuits because it needs to react so quickly that microcontrollers aren't going to be fast enough for that. Although those applications are becoming less and less common as microcontroller performance gets more and more advanced. And also where other IC devices offer necessary functionality, think about like sensors, light sensors, inertial sensors, temperature sensors. A lot of times you need to have the microcontroller interface to something in the real world And so we need to have some analog circuitry maybe to connect to those things. Or maybe not analog, but analog or digital circuitry to connect to those things. And we also have those things that need to be connected to. Those are going to be circuits that are outside of the microcontroller. Okay, so what's inside of a typical microcontroller? Here's an AT Mega 328, and I picked this one because it is the one that's used on that Arduino Uno board. We're going to get back to that in just a second. But if you notice here, here's the DIP package of that. It's a narrow DIP package with 28 pins. But you'll notice if you look at these, this is port D0 through 4. Here's port B0. Here's D6 and 7. Here's port B6 and 7. But if you look, these are all labeled PC, PD, PB, 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 PC. So these are all the different ports that are the I/O pins of that. And then other than that, you'll notice we have VCC and ground. That's power and ground. And here's AVCs. That's the analog kind of voltage supply. Here's an analog reference. But you'll notice that all of these pins labeled as port pins, those can be general purpose I/O, or you'll notice in parentheses off to the side of that, you'll notice that it has kind of these alternate functions that those can act as well. Notice there's a fairly rich set of things here. So this port C, for example, that can act as a port pin, meaning a digital I/O that you can just write stuff to, read stuff from. But it can also be an interrupt pin that causes this PC, which is a pin change interrupt, 14 to happen. So whenever that pin changes state from an input, it can actually interrupt the process and say, hey, something changed out there. So for something like a limit switch that closes on a machine, or a motion sensing device senses motion, it can interrupt the process. But it can also act as a reset line, meaning reset the whole program when this line gets pulled low. Here we have the same pin change on those, but receive and transmit for serial communication. This can act as an interrupt. This can act as another interrupt. Here's one that is OC2B. That's an output compare 2B. That's for a timer counter channel. But you'll notice every one of these can have these alternate functions. Like here's analog input 0, analog input 1. Another output capture. Here's SCK, MISO, MOSI, and slave select. That's an SPI interface. Here's SCL and SDA. That's a I2C interface. Here's more A to D converter channels up here. And so what you do is you basically configure this chip. It has some programming to configure the pins, whether you want them to be just I/O. And if it is I/O, is it input or is it output? Does it have an interrupt associated with it? And then it has alternate functions for those pins, some of which have multiple alternate function options. Now here's a diagram of it, of what's inside that chip. So everything inside the dotted line is inside that microcontroller. So out here, here are the port pins on the top. Here's more port pins on the bottom. These arrows are kind of an internal bus that carries stuff around. Here's the CPU inside this internal dotted line. And then here's all the other things we have here. The TWI, that's the I2C interface, two-wire communication interface, but you'll notice Eeprom in there. There's a UART in there. Here's SPI in there. There's an A to D converter in here, up here. And then here's an oscillator inside there. So all of this is what you get inside the chip. So the only things you need to really run this and get this to run for this design is this, and there's either a crystal on the outside, or notice it has an internal oscillator as well. You don't even need that crystal. So all you need to do is power this thing up and program your code into the memory inside of here. And this thing will run your program. So in other words, when it powers up, it'll start running code. Everything you need is kind of built into it, except for giving it power. And then how you connect it to and what you connect it to. All right, now this comes in multiple packages. So this one was the DIP package. Notice you can also get that in a TQFP or a QFN package. So smaller form factor, but a little square with pins coming out 4 sides rather than being through-hole mono with pins coming out 2 sides. But notice it's the same parts that are in here. Actually, a couple extra pins here, but notice it's got 2 grounds and 2 VCCs coming in. And so even though this is a 32-pin device, it does have a little bit more pins available, but some of those are taken up with additional ground and VCC pins. But again, same block diagram. So in other words, this is the same chip inside there, just in a different package. So this is surface mount, this is through hole. Okay, so back to the Arduino that's built upon that chip. Let's take a quick look at that. And again, it's a single board computer. I/O is based on the AVR microcontroller, specifically the Uno is based on this microcontroller. And there are other Arduino boards that are based on different microcontrollers other than this one. But the Arduino Uno is based on that AT Mega 328. It's easily programmed through that Arduino software. And the Arduino software environment, the programming language you use is C and C++. And it has added some things to make it easy to get started without you having to write a lot of the setup code yourself. It's done for you. And the Arduino, the abstractions for common tasks, we're going to look at some of those functions here, but it's basically like a little simple API we can use that's already done for us to make common programming tasks a little bit more simple. All right, so how does it work? Well, Arduino Programs, essentially, when you create a new, what they call it, a sketch, which is essentially just a program, but it comes with two functions that you're going to write code in. The first function is called setup. And so inside these curly braces, you would write your setup code. That runs once whenever the thing powers up. And then down here, we have loop. That runs over and over and over again. So you don't have to write a loop yourself inside here. So you could write code in here, and that's going to happen, and then happen again and again. So it's just going to keep calling this loop function over and over and over again. But one of the things to notice, if you're used to Eeprom, we don't have to pound include anything up here to get started. We don't have to write any code to set up the microcontroller and turn on its clocks or anything. All that's done for us. But if we want to change things, we just add things here. If we want things to happen repeatedly, we add them here. So pretty simple to get started. Now, what does the board look like? This is what the Arduino Uno board looks like. And you'll notice looking at it that we've got a set of pins, a little socket along the side here where you can plug wires into, or what I would suggest doing is plugging kind of those little pin wire connectors in there. And then along the side here, we've got another set of pins. And notice that what's nice with these is they're labeled on the silk screen, so we don't have to guess at what they do. And so you notice pin 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then over here we have our analog inputs, A0 through A5, so there's 6 of those. And over here we have a reset pin. There's 2 more up here that you can't read the label on, but those are I2C connections. And then up here, but the nice thing about this is that here's the processor. And you'll notice you can read AT Mega 328P. And if we go back to here, notice that's AT Mega 328. The P on the end was a little bit later version of the chip. It's a little bit lower power, but it's still the same. It's compatible. And then notice there's another chip up here. This is the chip that deals with the USB to convert USB to this and to reprogram this. So this is kind of like those boards we talked about had a programmer on board, but this is specific just for this chip and for the Arduino, not a generic programmer for any members of any family. So the idea is you can plug this thing into USB. That will power the whole board and act as the programming interface and as a way to communicate to the PC. Also notice there's a reset button up here in the corner, this little red button. So if you ever want to reset your program from the beginning, you just hit that button. You don't have to wire something into this pin over here. But if you did want to reset it with some other circuitry, you could plug a wire into here. If you pull that to ground and then release it, it'll also reset. That's essentially what this does when you push the button. All right, now this board is pretty small. It's like about that big. About the size of a little bit bigger than a Post-it note. And so to use this, all we have to do is write some code and put some code into the setup, put some code into the loop section of that, and then we can get this to do things. Now, again, those pins are labeled along the sides. We're going to look at that in a second. And here's a diagram that shows how they're labeled. So you'll notice these are all the digital I/O, and I've kind of, in this diagram, it includes the alternate functions of those. So here's SPI, here's I²C on those two, here's UART communication on these ones, here's analog pins over here, and then here's some power and ground connections over here that you could use to power other circuitry. And it also has some onboard LEDs here that you can interact with. This LED you can control. It's connected to pin 13. And this RX and TX are used whenever something comes through or goes out of the board through the USB for communication, or it's actually connected to the UART pins. But you'll notice that gives us the ability to see if it's communicating or if it's working. And we can use this LED for whatever we want. Okay, let's look at a little bit of code here and some of the functions. So first, there's this pin mode function that lets you pick a pin number, and these are the same numbers that are on the labeled on the board. So this is, hey, take pin 13, which is one connected to the LED, and set it to be an output. And then notice I can say digital write pin 13, set it high. So that would turn on the LED. And then I have a delay function, which delays for a number of milliseconds, because it's waiting for a half a second. And then digital write low, turn that LED off, and then wait another half a second. So in other words, this is going to turn an LED on for a half a second, and then off for a half second. All right, we can also read the state of a pin that's been configured as an input. So in other words, we can say pin mode. Now notice we don't have to write this function or any of these. Those already exist for us. The Arduino environment has those already made for us. So pin mode 13, set it to an input, and then we can do a digital read 13, and that's going to retrieve a 0 or a 1 from that port. Is it low or is it high? And return that to us. And when that returns that to us, we could then use that return value to do something. So in other words, here we could say, if digital read 13, in other words, if we read port 13 and it's a 0, it's low, then take some action. So we could write some code. So if that pin goes low, do something about it. Now, some other time-related functions. There's delay milliseconds, which is the one that we used back here. It's just delay. But then if you need a finer resolution than a millisecond, there's actually a delay microseconds, which is a much higher resolution. And then there's also a way to make things time-based in your code. That, like if you wanted something that happened every 10 seconds or wanted like a 10-second timeout before you do something, you can actually read the number of milliseconds out of this function. So kind of like look at a clock, get a value. But what it returns is the number of milliseconds since your program was last reset or powered on. And then micros returns the number of microseconds or millionths of a second since it was powered on. So both of those can be useful for making things that are time-based. Now, how do you talk to it over from the PC for development or prototyping? Well, there's this serial.begin you can do. This would usually be done in the setup section of your code. But then we also have the serial.print that then can send characters out of that after it's. So you have to start this. The 9600 is the baud rate of the PC serial port that you're setting up. So this is in bits per second. And this supports common baud rates, 9600, 19.2, or was it 19,200, 38,400, 157.6, and 115.2. So all those major baud rates that you're used to, but 9600 is usually good enough for prototyping. It's slow enough that it gives us the ability to send stuff in and kind of troubleshoot things pretty easily, but it's fast enough that we don't have a bottleneck there. And so 9600, he says, hey, when I say hello, it's going to get clocked out that 8 bits of the H at a rate of 9,600 bits per second for these. Now, so this is one way to write things out. Here's a way to read things in, is you first use serial.available. It tells you how many bytes have come in. And then serial.read reads one of the bytes, and you can do something based on that. So you can put that in the if statement and say, hey, if serial.read equal capital A, then they sent me the letter A, take some action based on that. And that can be kind could be used for communicating with the PC to talk to your board. All right, so here's a full example. This example, notice it says serial.begin 9600. That sets it up for this thing to send data or receive data from the PC through that USB port. And then here, pin mode 13, that sets the LED pin as an output. And then we set the LED low, we print out tick, we set the LED, or then we wait for a half a second, we set the LED high, we print out talk, we wait for a half a second. So this is going to be like tick, tock, tick, tock, tick, tock, and the LED is going to turn off with tick, on with talk. So off, on, off, on. And the rate that that's going to go is going to go through a whole off-on cycle once per second, just like a clock ticking. But notice how simple this code is. We don't have to do anything directly with the processor. All that's kind of being done before us behind the scenes. We just have to configure the serial port, change the pin 13 to the state we want, the type of pin we want it to be. And then down here, our code. And since this is already in loop, this is going to just happen over and over and over again. All right, here's another full working example. And you'll notice in this example, we've got an actual global variable being created, incoming byte. We set it to 0. Now this doesn't have to be an int. This could be a character type because we're going to use it to just read data from this. But again, we set up, in setup, we just set that up. Down here, I say, hey, if serial data came in other words, if the count of bytes that came in from the PC is bigger than 0, then let's read one. And then I'm just going to print out the byte that was received. And the serial.print line here, this incoming byte, DEC, that's just going to print it out in decimal for us. So super simple. Now, how do you get it set up so you can write your first program to an Arduino? Well, you install the Arduino environment, launch it, plug in your Arduino board. Under Tools, select the port number, the COM port that's associated with that board you just plugged in, and then select the type of Arduino board it is. In your case, if it's the Uno board like we talked about, you would set it to that selection. And now you're ready to write the code like this. Create a new project or a new sketch, write your code in the setup, write your code in the loop, and then click the little play button at the top to send it to the board and run it. And that's pretty much it. So you could change that code to do whatever you want. Now, the other thing about Arduinos, this is a whole family of different products that are compatible with that. So I didn't include the Uno on here because we already had that over there, but you'll notice there are other ones on here as well. There's this Arduino Mega, which is based on another family member, but notice that it's a much longer board with a lot more I/O. It's got pins on the bottom here, pins over there. It also has a lot more code space, a lot more memory. And so that's a larger board that does stuff. Then there's also one that has Ethernet capability. Oops, let's go back for a second. There's this Arduino Mini, which is much smaller, but compatible with that one we just looked at. There's this Arduino FIO board, and then there's this Arduino Nano, which is even smaller yet. And it goes all the way down to these little Beetle boards down here that are really, really tiny boards. And this is actually larger than it is. Those pins there are the same width apart as the pins are over here. So it's just enlarged to show texture, as they'd say on a cereal box. But you notice that I just enlarged that so it's easy. So this is a really small board that still has a significant processing power, but obviously less in the way of I/O and pins on the outside that you can access. Arduino Nano is pretty good. And then there's a whole range of these Arduino boards here that notice these ones have wireless modules and Bluetooth built into them onto that board if you needed wireless capability. So you can pick the right one for the right job. And this isn't all of them either. There's more than this out there as well. Okay, now let's switch gears and look at something a little more powerful, but also easy to get started in and easy to program. A little bit more complex than the Arduino, but not significantly so that you couldn't get this to work without too much difficulty. And this also has the advantage of being able to be programmed in a programming language called Python. And Python is a nice choice for programming because it's even easier to use than Arduino with C and C++. It's a simpler language to get started in for most people than something like the Arduino. Now, the other thing about the Raspberry Pi is it's a much more powerful processor that's on here than on the Arduino. The Arduino, if you look at that board back here, okay, let's go back to that for just a second. This board here, this board, I believe, is running at 16 megahertz. So in other words, 16 million operations per second. It's got 32K worth of program space, and I believe 1K worth of RAM. So not a small amount of program space, but also not a lot either. And also the 16 megahertz, 16 million operations per second is blazing fast as far as human standards, but as far as computers go, it's, I don't know, that's maybe 10 times faster than the original IBM PC, maybe more than that because it's a RISC architecture. But it's fast, but not as fast as something like a PC or something there. So when we go back to that Raspberry Pi, notice that this is a quad-core 64-bit microcontroller that runs at 1.5 gigahertz. So this thing has some serious power to it. This runs a full Linux operating system that runs off of a micro SD card that's used for both storage, like a hard drive, but it's also used for the program stuff that you put on there. It's got Wi-Fi built in, it's got Bluetooth built in, it's got Ethernet built in, it's got 2 HDMI video interfaces down here, so you can plug 2 monitors into this thing that are full 4K resolution capable. If you plug it into a 4K TV, you could actually drive 4K output from this. It's got 2 camera interfaces through this little port here. The cameras aren't built in, but you can buy them and plug them into that little flex cable connector there. And it also has 2 DisplayPort interfaces on this connector. Also notice it's got 2 USB 2.0 ports, 2 USB 3.0 ports, and it's got Ethernet built in. So there's a lot of stuff built into this thing. It's a very powerful single board computer, which is about the size of a playing card. Like a pack, think of a pack of playing cards. It also has audio output built in. And it's got a lot of general purpose I/O with this connector here that we can connect to whatever stuff we want it to be connected to. Okay, here's a closer view of that pinout. And again, just like with the pins on the AT Mega microcontroller we looked at earlier, these have alternate functions. So notice GPIO2, that's SDA of I2C interface to talk to some other chip or other devices. GPIO3 can, so in other words, that pin 3 or GPIO2 and 3, those could be used as general purpose IO pins. They're either low or high, or they could be used as the I2C interface. And notice that some of them are just general purpose IO, but here's a transmit and receive here. For UART connections, down here we've got, here's some SPI bus connections. Here's a pulse width modulation channel over here, another one over there. So notice that you can set this up to do a lot of different things. One thing that is notably missing from this is A to D conversion, that there is no A to D converter built in, but there are I2C or SPI A to D converters, so you could really just connect them to here or here and talk to them through that. All right, how do you get started with this? Well, you install the operating system on a micro SD card. To download the operating system, basically you just go to raspberrypi.org downloader. There's a special tool called the Raspberry Pi Imager. You download that, and then you can pick which kind of image you want. There's a couple of choices there. Most people use Raspbian, which is kind of the standard Raspberry Pi configuration. But there's also another one that makes this thing act as an arcade machine, it has an arcade emulator built in, and when you power it up, it automatically boots into that. But I would suggest you just downloading Raspbian and put it on a micro SD card using the imaging tool. And then once you do that, you just plug the card into the Raspberry Pi, turn it on, and it boots up. And when it boots up into the Raspbian OS, it actually, if you plug that into a TV, it'll bring up a desktop just like you would with a PC. If you plug a keyboard into or a mouse into one of the USB ports, then you basically have a full PC all on that one Raspberry Pi board that you can do stuff with. Now, how do you connect to it? Well, like I said, you could plug a mouse, a keyboard, and a monitor into it and use it just like a computer. Or if you don't want to set all that up, you can actually talk to it through your laptop in a couple ways. One, you could set up a VNC client to talk to it. And the VNC client will give you a desktop just like you would have from a monitor being plugged in, but it'll give it to you in a window on your PC. And when you're over that window, you can move the mouse. It'll move the mouse on the actual Raspberry Pi system. If you click, it'll click. If you type, it'll type. So it's just like any other VNC is kind of a virtual machine network client thing. So you can actually talk to that just like you were if you had done option 1. And there's a little guide to how to set that up here. There's a couple things you have to do to set that up, but I set that up on mine. It's super easy to do. Now, the other thing here is you can also use Putty connect to the Raspberry Pi over a terminal, and then you'll get a command line interface to do stuff on it. But since it is a full Linux computer, you can do pretty much almost anything you want through that command line interface. You can write a program, you can save the program, you can run the program. The only thing you're not going to be able to see through that command line interface, if you wrote a program that did graphical things, you won't see that through there. Okay. Now, so that was step 2, was connect. Step 3 is to write code for it. So since that Raspberry Pi is a full Linux system, you can write your code in a variety of ways using any tools that you could on Linux. So C and C++, it has built-in compilers for that already come on Raspbian. It also has both a Python 2 and a Python 3 interpreter that are included, and it includes a little really simple Python development environment called Thani. And that's like a little IDE. You type code in, you click the play button, it runs the code. So super easy. There are other languages as well, including there's a build of OpenPLC. If you used to program with logic controllers, you could run that, install that, run that. And then you could do ladder logic and build the thing, and it would act like a programmable logic controller that you're used to programming. All built into that thing. Okay, here's the pinout of that. So again, notice that in this case for the pinout, first thing we're going to need to do, and here I'm putting the code here in using Python, because for using this, Python is a little bit easier to learn, a little less dangerous to program in, meaning that you're going to have fewer bugs and fewer errors if you use Python. But to show you how easy it is to interact with the I/O on this, import rpi.gpio. So you import the GPIO module. Then after you've done that, you call gpio.setMode. Now there's 2 different modes here, and this isn't like the pin mode of the Arduino. The set mode here is how do we want to treat the pin numbers on this. And you'll notice there's a pin number over here, like 1, 2, or 1, 2, 3, 4. So there's a pin number, but then also there's this GPIO number, which is pin 2 is actually on pin 3, GPIO 3 is on pin 5, GPIO 4 is on 7, and so forth. So the question is, do we want to number it according to the what they call the Broadcom, because that's the type of chip that's on here, that type of pin numbering scheme, or do we want to use the pin numbers that are on the actual board? So it gives us the option, do I want to think of it as GPIO 2, or do I want to think of it as pin 3? So it gives us a choice. So we have to call one of those, but then after we do that, then the pin number we use will go to the right place. So here, this GPIO setup 23, that could either be pin 23 here, or it could be GPIO 23 over there, depending on which one of these we did. So we just have to make sure we're consistent and we do that right. But this GPIO setup here, we say pin 23, and here we say set it up as an output. Very similar to what we had on the Arduino, but a different function to do that. Now down here we could set it up a pin as an input, say GPIO.setup 17, GPIO.in, and then here pull up, down, we're going to set it up to be pull up resistors. In other words, if nothing's connected, that input, rather than just floating around, it'll get pulled high with an internal pull-up resistance. So it'll default to high. If we pull it low, it'll go low. And so this can allow us to have a default state rather than having a pin just floating around. All right, so simple few lines of code. Import that, pick which pin numbering scheme you want, and then use the pin number and whether we want to set up as an output or an input. Now, to set an output pin state, so in other words, to set a pin that we've already configured, we already set it up to be an output, like here's pin 23. If we want to set it low, we can say GPIO.output 23 GPIO.low. Or you could also put a 0 here. If we want to set it high, same thing, but GPIO.high, or put a 1 there. Now to read the state of an input pin, we just do GPIO.input, give the number of the pin, and then indented underneath it here would be the actions to take if that pin, in this case, would be high. It also has the ability to set up pulse width modulation on a pin and have the thing handle it automatically. So here, PWM1 equals GPIO, PWM18, 100, that's a frequency of 100. That's saying take pin 18 and use a frequency of 100 on that. And then down here, you'll notice it doesn't do anything when we call that until we start it. So PWM start, we'll start getting a square wave with a duty cycle of 50% there. And then here, duty cycle 30, that would change it rather than from 50%, rather than half high, half low, to 30% high, 70% low. And then if we can change that anywhere in our code we want. So we can go to full duty cycle to minimum duty cycle, and then we can do a PWM to stop when we're done. Okay, so here's an example Raspberry Pi general purpose I/O program. So here, I do that. I set up the pins. I gave the pins names: pulse width modulation pin, LED pin, button pin. And then notice I use the mode BCM, the pin numbering scheme. Back here, that would be these ones in the orange, rather than the ones that are in gray. But then after that, we just say, hey, set up the LED pin as an output, set up the pulse width modulation pin as an output, set the pulse width modulation to have a frequency of 100 Hertz, and use that pin number, which is 18 that we set up there. Set up the general purpose I/O button pin to be an input, and have a pull-up resistor on that, internal pull-up. And then that's continued on the next page. And then here we are actually going to do something with that. Set the LED state to be off by default. Start the pulse width modulation. And then here's some code. What are we doing inside of here? We're saying, hey, while one, in other words, run forever. And I have that in a try except, so we can do Control-C to stop the program from running if we want to. And what we do inside of this code, we're basically saying if they press the input button, then change the duty cycle to that. So that's if they press the input button, and then set the LED to low. If the button is pressed, then change the duty cycle to 100 minus that, so that inverts it. And notice since we started at 95, that would change from 95 to 5, and then back to 95 again. When we press and release the button, depending if the button's pressed or released, we also manipulate that LED each time. And then if we ever break out of this, then we stop the pulse width modulation and do GPIO cleanup, which will turn all the outputs back to inputs and basically go back to not doing anything. But notice, pretty straightforward. It takes a little getting used to the different commands that you need, but it's not really so dissimilar to the Arduino. And this is in Python, so it's a lot easier to experiment with and write code and have it not be problematic. Okay, also the Raspberry Pi supports SPI bus to talk to other devices, and I2C bus to talk to other devices. And you can do that from Python. The two modules from that, there's an SPI module, import SPI dev, and then the I2C module, import SM bus. But then after you've imported those, they're very easy to use. Here's a little link to how to do that. And to show you where those pins would be for the I2C and SPI, here's the I2C pins. down here, there's two SPI ports, SPI 0, SPI 1. Those are in purple here for the SPI, this cyan color for the I2C. And it actually turns out that there are other I2C and other SPI interfaces as well on here, but you have to enable those. So I'll let you worry about that or figure that out on your own. If you ever needed two I2C buses, for example, there's a way to turn on other I2C buses as well on other pins that aren't currently labeled on here. But you have to make a couple of configuration changes to a config file on the device. Okay, a few other cleanup things here. We're a little over an hour today, and I want it to be at about an hour. But a couple final cleanup things here. Raspberry Pi Model 4 is here. That's the one we were just looking at. But here's a Raspberry Pi Pico, much smaller. This is a $4 board, but it has a very powerful chip as well on that, but it does not have a full operating system like the other one. This one's more like the Arduino that you write your code and compile it and then upload it to that. But again, this is I think a 1 gigahertz chip or something on there, so very powerful for $4. Here's a Raspberry Pi Zero W. This says Raspberry Pi Zero does run a full operating system, and it has, the W means wireless, so it also has Wi-Fi capability built onto that board. And so that's a $15 Wi-Fi capable board that you can get, and also it has HDMI on it. So this is kind of like a lower powered version of this with a little bit less peripherals, but notice it does have a place you can solder wires or a connector into, just like this. Same kind of connector. So this is $15 for that. And then over here, all the way on the right, we have the Raspberry Pi Zero rather than Zero W. That's $5. And it has all of the same power this does, but no Wi-Fi built in. But if you just needed a cheap, high-powered processor to do stuff, this is actually a really good value at $5. And then if you wanted to build your own custom board, that chip that's actually used on the Raspberry Pi Pico, you can buy those individually. They're 70 cents a piece, and that's a dual-core 133 megahertz chip, I believe. That I forget how much RAM it has, but it's a lot. It's like 2 meg of RAM or something like that on it. But the program storage for this actually is off chip on another little chip, like right there. But for 70 cents, that's a whole lot of processing power if you ever wanted to build your own board for that. Now, all of these, the Raspberry Pi Zeros and the Model B run a full operating system, but the RP2040 and the Raspberry Pi Pico, they're programmed using C and C++, but you can also use MicroPython or CircuitPython, which are kind of special builds of Python that make it easy to do the same kind of thing we were doing in that code over there, but on these boards without a full operating system running. Okay, and if you want more information on those, raspberrypi.org has tons of documents, sample code, getting started guides, how-to, stuff like that. So if you're interested in that, look there. So I would suggest one of those two things would be a good choice, but really any of those other things, the Teensy, those other development things like the STM32 Discovery board, or the Texas Instruments TMS 240 or whatever that is boards, those are all good boards to get started. But if you want to use something like a simplified environment, I'd suggest Arduino or the Raspberry Pi, and then use either C or C++ if you're comfortable with that, or Python if you're kind of new to it. Okay, that's it for today. The other thing I want you to do is your proposals are going to be due. You have a week to work on those and get those submitted. But I want you to narrow down your ideas set from what you did for Lab 1. I want you to narrow that down some, try to get that submitted for before next class, because I want to approve those and then get you started on that. Also, those of you who are in the ETech 4301, keep in mind that the original schedule had us meeting once a week, only on Mondays. Really, we're supposed to meet twice a week, Mondays and Wednesdays. So start building that into your schedule as well, because I want to see you guys coming in and working on your project, at least initially, until you get started and are kind of flowing on it. I want you to come in and get started, talk to me about it, and let's get things underway. Also, keep in mind if you have mechanical things that you need to do for your project, we'll talk about that later on. But I want you to do some serious thinking about. We don't have a lot of time for this, so make sure to limit your project to something you can get some prototype working within the time we have left. Okay, and that's all I want to talk about today. So stay safe. I apologize for being not in class again, but COVID is everywhere, and I have another family member that's tested positive. So for this week, we'll probably be remote, work on your proposals, try to narrow things down. And then next week, we should be back to being in person. I don't have COVID. I'm totally fine. So I have to quarantine this week. Should be back next week. Okay, that's it. Everybody stay safe, and I will see you hopefully next time. If you need anything, shoot me an email, send me a text message. We can set up a Zoom, whatever. I'm there if you need something. I will not be in office hours because I'm not allowed on campus until next week. But if you need anything, you got my contact information. Get a hold of me. That's it.